Oh, thank you. Yeah, so this is kind of work that's coming out of my PhD. So I wanted to highlight some of my great collaborators, and especially Erica Tiggerson. She just finished her first year of grad school, and I'm really lucky that I get to work with her. So I just wanted to give her a shout out. So I'm going to be talking about some new sources we found in M87. But to start off, I should talk about, like, first, what are ultraluminous X-ray sources? And the kind of simple explanation is that they are off-nuclear X-ray point sources with luminosities greater than about 10 to the 39 ergs per second. And we pick that because that's greater than the Eddington limit for a 10 solar mass black hole. So it means that whatever's going on here is really exciting. So they've mostly been successfully identified and studied in young star-forming galaxies. The picture below is kind of the classic example of one. And they they're thought to have a very high accretion rate that's fed off of a massive donor star, because again, they're in star-forming regions of galaxies. And there's mounting evidence that the compact object might be a neutron star. So that's pulsating ultraluminous X-ray sources. So in 2014, a paper by Becchetti that was just really, really neat discovery found pulsations in the X-ray light curves of one of these ULXs, which means that it has to be a neutron star rather than a black hole because you need a surface. So this means it's accreting at hundreds of times above the Eddington limit, which is really crazy. And so some possible explanations for this are maybe geometric beaming or maybe high magnetic fields, and something like that. But I'm not here to talk about those sources. In fact, I'm going to kind of talk about their exact opposite, ULXs in globular clusters. So since 2007, around 10 ULXs have been successfully identified with globular cluster host. Now, these are associated with elliptical galaxies. So there are a lot of key differences here, which I'm going to set up. So one of the key differences is that we don't have massive donor stars because globular cluster systems are an old environment. Second of all, the ULXs in star-forming regions, you could kind of say that they form together. In a way, they're social distancing. When you're in a globular cluster, it's this dense stellar environment, and there's like crowding and like dynamical interactions with each other. It's a very, very different place. And so that means that the evolution information history is very different and really dynamic and just very interesting. So there's kind of these huge differences in environments between the two. And based on a lot of studies for the neutron star ULXs, the conditions that seem to be required to form a neutron star ULXs are not met in this crowded globular cluster system. And it also kind of implies that they're actually likely to be best explained by having a black hole accretor. So even though they're like weird and really hard to study, I think they're worth going after. So like, what else can we learn from them? So they're going to have really interesting accretion physics because they're taking these low mass donor stars and accreting at fairly high rates. But if they really are best explained by black holes, they can actually help inform on the progenitors of the merging black hole systems detected by LIGO. Now, what's interesting is the debate of whether or not globular clusters can even host black holes has been this ongoing thing since the 1970s. Spitzer actually was the one that said, okay, I think, globular clusters, old environments, great places to form a black hole, but because of all this dynamical interactions, they're just going to get ejected. Newer simulations, especially by people at the Northwestern group, are showing this may not be the case. And we really want to know if globular clusters can host black holes, because if you want, if there's studies saying that these black hole binaries could have been formed in globular clusters, and Kyle Kramer's work is a great example of that, then you kind of need to go after observational evidence to study black holes in globular clusters. And so there's actually a lot of people at Michigan State will study globular clusters in our own Milky Way, and then also the Muse group has actually dynamically measured, I want to say 2 to 3 black holes in NGC 3201, which is another globular cluster in our own Milky Way. But the methods that they use don't really work outside of our galaxy, which is why we're going after these ULX sources. So I'm just going to give a little bit of background on the previously studied sources. And one of the things that's really interesting is that, so 2 of them have found to have this really unusual optical emission beyond the host cluster continuum. So this is an object example from an object in NGC 1399 that was published in Irwin et al. 2010. And what you're looking at here is an optical spectrum. So you got wavelength and intensity, and you have this globular cluster continuum here, which is nice. And then you have this narrow emission that rises above it, and you have O3 and you have N2. So they're both forbidden transition lines. And then our favorite source, RZ2109, has this crazy spectrum. It is really, as far as we know, the only source with a spectrum like it. Is very unique because you have, this is, again, this is the O3. So it's a forbidden transition line, but it's actually broadened here. So this is the 5007 core. And this is the only source we know of with this broad structure. And the structure is evolving over time. But again, I'm not, that's background. I'm not here to talk about these. We're going to talk about M87. So it is best known for its jet, but it's also home to about 15,000 globular clusters. So if you are looking for a rare globular cluster source, this is the perfect place to go looking. And again, across the search of several galaxies, previously we'd only identified 10, so they're pretty hard to find. Super exciting, we found 7 new sources. 6 are actually near the galaxy's center, and then another one is in a field about 19 arc minutes away. And then unfortunately, because of this jet and like a very active supermassive black hole, we have this crazy background to deal with. So the sources in the central region are harder to study, but I still, again, think it's worthwhile. So what makes a source interesting? So there's a few things. So one is if it has a very metal poor or a very metal rich globular cluster companion. So if it's metal poor, it'll appear bluer because it has fewer redder stars. And then if it's metal rich, it'll appear redder in color. So there's a way you can measure this, which I'll talk about in the next slide. But another thing that's interesting is if it shows extreme variability. So if it varies like within an observation on the time scale of hours, that's interesting because out of the 10 previously studied sources, only 2 have shown variability on the time scale of hours that we've seen. And then another option is if it shows variability on the time scale of decades. And we do have some sources that are extremely variable long-term. And we've also had one source that was on for a while and turned off. But other than that, we haven't seen any sources turning on, which I find interesting. If it has a very hard or very soft spectrum, or if there's spectral evolution over the course of many observations. Those are all interesting. So the first question is there anything special about the host clusters? So what this plot is showing you is on the y-axis, I'm showing its Z magnitude, so how bright the cluster is. Remember, because we're backwards, my axis is backwards, so the brighter stuff is up here, down here is fainter. And then on this x-axis, G minus Z is the color or the metallicity. So if it's redder, it's going to be over here. If it's bluer, it's going to be over here. And what I find interesting is that we actually span a fairly large range of metallicity. Although as a caveat, some of the larger or brighter cluster sources may be tidally stripped galaxy nuclei. We don't have a good way of distinguishing that. And some of them are at the mass limit for that. But still, this is like a neat result. So the next question is, what about variability? So we did find the 3rd ever ULX globular cluster source to show variability within an observation. And again, it's really interesting because of the past 10 sources that were studied, 8 of them show these really boring light curves where nothing was happening. So it's really exciting to see this one do that. And it's kind of hard to tell, physically, what does this mean about the source yet? I feel like we're still creating a museum of weird objects still. So that was exciting. And then another thing we care about is long-term variability. So I just put, this plot was kind of hard to make in a way that was not messy. So I put some of the objects on there. So these are all M87 objects. Some of them are faded out because they're not the ones I want to highlight. But what I find interesting is that we definitely have these sources that are getting brighter and then peaking. You can see that some of them went above 10 to the 39 or near. So this is just really interesting variability, and it might be that we are catching these sources turning on. So they would definitely be interesting to follow up now and see what they're doing. So we're going to talk about X-ray spectra next. So here's the thing about my spectra is that they are not the most beautiful spectrum. This one looks nice because it's like probably 300 kiloseconds worth of data stacked. But when you have really sparsely populated data, you can't really fit like detailed models to it and gain physical intuition about the nature of the source. You kind of just fit really simple models and see, okay, do these change across observations, or do they change maybe with the X-ray luminosity? So I just fit like a thermal disk model, so disk BB, a power law model, and then I also tried adding the two to everything and just try to see how well do these work, you know, do the data like them or not, and do they change across observations? So to visualize this, I found the best way to do it is you plot X-ray luminosity on this axis. So this is 10 to the 38 ergs per second here, 10 to the 39 up here. And then when it comes back again on the x-axis, there we go. So the x-axis shows the temperature. So that's kind of the inner disk temperature for the disk BB model. And I like to think of it as a parameter for the spectral shape. So I did not keep my values down here, which was silly. But when it comes back again, this first tick is about 1 keV. And you can see that the M87 sources are kind of spread all over the place. I'm not sure how well they show up, but there are some faded out sources such as here. So these are data fits of the same model across observations of the previously studied sources. And so even though there's not really a discernible or, you know, trend of what these do, for instance, it would be tempting to say, oh, you know, I could fit a line across here and say that temperature and luminosity are correlated, because of the huge uncertainty in the error bars. That's not, you know, statistically correct to say, like, we can't prove that. But one of the things that's really highlights is how much some of these previously studied sources jump out. So in this circle here, you can see there's a source here that's a lower temperature. And then we have this other source over here that is a lower temperature. So none of the M87 sources really get as low as a temperature of these previously studied sources, which is interesting. And now for the other model I fit, which is the power law, so that's kind of a harder model. I, you know, again, made the same plot. So we have X-ray luminosity on this axis, and we have the power law index down here. And again, you know, like, this is a kind of a messy plot. The M87 sources go all over the place, but there's a source in NGC 1399 that also really stands out. So it's kind of safe to say we know what these sources don't do.
3 minutes.
Oh, I'm done early, I guess. So the takeaway from this is that it's very exciting. We almost doubled the known samples of ULXs hosted by globular clusters. We have some really exciting finds, just highly variable sources, and the ones that like look like they turned on. And because we now have a little bit larger of a sample, we are kind of getting closer to establishing like what is common or like what is unusual. You know, like we showed, what do these sources not do? And I think there's a lot of really interesting future work on following up on these sources, both in the optical, looking at the optical spectra of some of these clusters to see if any of them have emission beyond the cluster continuum, like the two sources I showed earlier. And then also I'd like to follow up on more of the transient ones, just because, you know, it's really hard to study transient X-ray sources because you don't know what they're going to do when. So they were just really exciting to come across. That's all.
Okay, thank you very much, Kristen. A very nice talk. Let's see, there's no questions in the Q&A yet. If you have any questions, please post them there. But I have a question about your variability or your transient behavior. And one slide you showed basically a few epochs, right? With right, this one, correct. So I mean, it is hard to say because you only have basically a few epochs here, but because you mentioned something about the different timescales of variability, I mean, the variability that you would see here from one epoch to the next, could that just be that there is just a lot of variability, have it in a day or within hours, and you just happen to get those snapshots? Or do you really think that there is, besides the kind of intraday or shorter timescale variability, that there is also really a longer timescale variability?
That's a really great question. So I'm going to go back to here, the slide. So this is I looked at all of the light curves of the M87 sources, and all of them except for this one were pretty much flat. Mm-hmm. So in the one that was not flat is actually this one right here. This was the one that showed variability. Gotcha. So that means that all of these didn't show variability like with, you know, like within the observation. So I don't think that we're looking at snapshots unless the variability happens on longer timescales than the observations. Like that is not something we could rule out.
Gotcha. Gotcha. Okay.
I've actually got a follow-up question on variability. Obviously, it's very exciting that we know now that some of these are X-ray pulsars seen by NuSTAR. Am I correct in assuming that none of the data here is good enough in order to test for pulsations, or what would be required in order to look for pulsations? Could you do it with something like Athena or Lynx?
So I think a huge issue with looking for pulsations. So first of all, is like, I think some of papers have shown that the pulsations in the known pulsating ones are transient. So that is tricky to, we can't look at something and say, oh, it doesn't have pulsations, we're off the hook of it being a neutron star. But I think the bigger issue is that these are more distant sources, right? So these are sources at 16 to 20 megaparsecs away. The sources that are being studied and observed with to show pulsations are more like on the order of 10 megaparsecs away. So they have, even though maybe they're similar X-ray luminosities, mine have a lower flux. And so it is harder to do a lot of those studies with it.
Okay, so see, several questions came in at the same time. First question from Craig Hankey. We've seen non-globular cluster ULXs largely fall into two categories. Transients that go to a few times 10 to the 39 Earth per second, which look like normal black hole Lomas X-ray binaries that go slightly super Eddington, versus often persistent ULXs that are much brighter and don't appear like normal black hole Lomas X-ray binaries. So the question is, are your objects inconsistent with the first category?
So that's also a really great question. And I would say that, I'm gonna throw one of these objects under the bus. I think this red one here, you can see it spends most of its time below 10 to the 39 and it dips up. So I would say that one would be more similar to the first category he's talking about. Whereas this faded out purple one does spend every observation, we've looked at it. And this is there's a ton of archival Chandra data on M87 out there. I went through a lot of data. So this probably spans about 16 years, I think. And so this one, every time we've looked at it, it has been above 10 to the 39. So it seems, I think his question was saying that there's a category of the ones that are below and dip up, which we have just seen. I don't think we've found those before in the previously studied sample. And then we also have this population that kind of hangs out above 10 to the 39.
Okay. Let's see, then there was a question by Daryl Haggard. Have you given any thought to the detectability for gravitational wave sources? For instance, merging black holes detected by LIGO in these globular clusters in M87. Seems like an interesting population to monitor since we know distances sort of.
That's a really interesting question. I have not thought about that at all. I'm actually I have thought a little bit about the LISA sources because I think, again, Kyle Kramer, I believe, had a paper suggesting that if you had a ultra compact X-ray binary, those would give off chirps detectable by LISA. And one of the previously studied sources, RZ2109, there's really a lot of strong evidence that the donor star in that case is actually a white dwarf. So that would be an interesting LISA source, but I'm not sure. Yeah, I'm not sure how it would work for LIGO, how you would tell.
Okay. Then a question by Knox Long. How do you know that some of the non-variable sources are not actually background AGN?
So it's because we matched them to globular clusters. So if you read Tom Macaron's 2007 paper, it's pretty much if you match it to a globular cluster, that means that it's a very small, I want to say 10 to the -4 chance that it's a mismatch with an AGN. So because we have an optical counterpart to it, we can rule out that it's a background AGN.
Gotcha.
Mostly.
Okay. And then the last question by Dacheng Lin. In M31, many bright sources are found in globular clusters. Shouldn't they be in neutron star LMXPs? It is hard to imagine that they are all black hole X-ray binaries.
So I don't think the objects in M31 get as bright as these. Somebody can correct me on that, but I don't think they get as bright as these. But I think a lot of this work has to do, so really the only globular cluster ULX that's been as like well studied in optical and X-ray for a very long time period is RZ2109, the source I talked about here. So this one is the one that we think has a white dwarf donor star. And there's a really interesting paper by Ross Church published in 2018 where he talks about like the formation of an ultra compact X-ray binary in a globular cluster. And if indeed, you know, it is a white dwarf donor star, then you are actually unlikely to get a stable formation of a neutron star plus a white dwarf in the globular cluster environment, but you are likely to get a stable formation of a black hole plus a white dwarf in the environment. But I think the bigger problem is when we talk about, like when you read papers about people talking about neutron star ULXs, the way they explain how something, you know, like with so little mass can accrete at such a high rate, it invokes a lot of things that you can't get in a globular cluster, like a high mass donor star, and also the magnetic field. If it is powered by a big magnetic field, that's going to be an issue because when you are in a globular cluster, you're old, and so that means that your magnetic fields are going to decay.
Okay, these were the questions. Thank you very much, and good luck next week in your thesis defense.